Well, hello everybody, Dave here, and today we're going to talk about the mirror equation and lenses. Hopefully you've already taken a look at mirrors and ray diagrams and this idea of magnification, because those are going to be very useful to you here in this lesson. As a reminder, let's take a look at a typical ray diagram for a concave mirror. You can see that we have the object on the left-hand side outside of the center of curvature, labeled by C. You'll also see that halfway between C and the mirror is F, which is our focal point. And now we have our three rays to determine where the image is and determine it in terms of size and whether it's upright or inverted. And you can see that the first ray is a ray parallel to the principal axis, and when it hits the mirror it bounces through the focal point, and that gives us ray number 1. Ray number 2 now is from the top of the object down through the focal point until it hits the mirror, in which case it bounces back parallel to the principal axis. The third ray, which is one that we don't always see in a ray diagram, is the one from the top of the object through the center of curvature until it hits the mirror. And you can see that the convergence point is where we've labeled this particular image. Now, taking a look at this ray diagram, we are able to make some determinations. We can determine that it is a real image because it is something that is in front of the mirror, which can be projected onto a screen. That's opposed to a virtual image, which is an image that is behind the mirror, which when you put some sort of screen in front of that mirror, the image itself will not be projected onto it. When we talk about the size, we can see pretty clearly in the ray diagram that it is a reduced size, which we'll talk about when we get to the magnification equation. And because it's pointing down instead of up, we refer to this as inverted instead of right side up. So these were the physical properties of the image that we were determining in a previous lesson. So with the magnification equation, we can actually start to quantify exactly how small or large the image is. You can see that magnification is equivalent to the ratio of the image distance over the object distance, or the image height over the object height. But you'll also notice that in the case of the image distance and object distance that we have this negative sign hardwired in front. You'll remember in physics that negative signs usually mean something other than what they represent in mathematics. And in this case, the negative sign is meant to represent the inverted nature of the image itself. So if we had an upright image, we would actually see this magnification as a positive value, not a negative value. So you can see that we've plugged in the values that we had from our previous question to get a magnification of negative 0.67 times. And what that means is it's smaller and it's inverted from its original position. So if we take our original ray diagram and we label things according to angles and distances, we can derive an equation that relates these distances to the focal point itself. So you'll notice that the first thing we've done is taken a ray and we've labeled the angle alpha. And we have two different ways of relating alpha based upon the triangles that are formed. Now it's important to recognize that we know that those two angles are equivalent to each other because they are vertically opposite to each other, and this is a basic angle proof. And so if we take the one triangle, we can see that the tangent of alpha is actually our object height divided by the base of that triangle, which we've equated to P minus R. And for the second triangle, we know that the image height, which we've labeled as H prime, is divided by R minus Q, and that's going to give us the base of that smaller triangle. We know now that because these angles are equal to each other, that we can actually equate these two quantities to each other, and that's what we've done up top. We've also rearranged it a bit so that instead of having it H over P minus R, we've done H prime divided by H, and we end up with our equation that you see before you. Now we can actually implement the magnification equation to come up with our expression of R minus Q divided by P minus R is equal to Q over P. From here, we have to remind ourselves that the R value in this case is actually the radius of curvature, which we know is 2 times the focal length. And when we plug that value in for R, do a little fancy algebra, we actually get our equation of 1 over P plus 1 over Q is equal to 1 over F. Now these notations are a little different than what you've seen. This is the classic notation that you're going to see, that 1 over the focal length is equal to 1 over the image distance plus 1 over the object distance. And depending upon whether we're dealing with mirrors or lenses, we're going to end up with a different value of our focal length. With a concave mirror, we know that it has a positive focal length, but with a convex mirror, it's negative. When we get into lenses, you'll find out that a converging lens has a positive focal length versus a diverging lens, which has a negative focal length. The sign convention is going to be essential when you use this equation, so make sure that you note this somewhere in your notes. So when we're talking about mirrors on their own, you can see that we've laid out these sign conventions for you. That when we're talking about an object in front of the mirror, that's going to have a positive value. If we're talking about an object behind a mirror, then we're going to call that a negative object distance. When it comes to images and focal lengths, this is exactly the same convention. The important thing to recognize, of course, is when we're talking about image height and magnification, that if it is an upright image, we are going to have a positive value for the image height and a positive value for the magnification value. The opposite is true when it comes to an inverted image, that we're going to have a negative image height and a negative magnification. So make sure that you make note of this moving forward, because lenses are similar, but a little different because instead of a reflection, refraction is taking place. If we use this equation in an example, let's assume that a concave spherical mirror has a focal length of 10 centimeters, and we want to locate the image for an object distance of 25 centimeters and describe the image's characteristics. So this is a classic type of question involving mirrors or lenses, because they've given you some information about the distance away from the object, and they also want you to describe the image's characteristics. So this is where the sign convention is going to be key, because we're going to refer to things as enlarged or virtual or inverted depending upon what information we have. So if we take our mirror equation and we plug in the values that we know, we can see that all we don't know is the image distance, and doing a little simple arithmetic, we end up with a value of 16.67 centimeters. So we know that because our focal length was 10 centimeters, our center of curvature would be 20 centimeters. So we know that this particular image is in between the center of curvature and the focal length. And since the image distance is a positive value, we know that it's a real image because it's a mirror, and we know that it's in front of that mirror. So let's remember then that for real images, we're talking about a positive image distance versus a virtual image, which is going to be a negative image distance. A classic demonstration of this would be putting a piece of paper in front of a mirror and actually noticing that the image is being focused on that piece of paper, as opposed to a convex mirror, which results in a virtual image. There is no image formed on that piece of paper. So it's a nice little demonstration that you can deal with at home. So if we're talking about size and orientation, again, we've typically just talked about it being inverted and reduced or whatever the case may be, but now we actually have a way to calculate this, because we can use our mirror equation. We can solve for the image distance, which in this particular case is going to be negative 10 centimeters. And that negative tells us that the image distance is actually behind the mirror, which already implies that it's a virtual image. If we take a look at the magnification equation, we already know the object distance, but we also have this negative image distance, which results in a magnification of 2 times. You'll notice that it's a positive value, and you'll notice that it's greater than 1, which means that the magnification is actually an enlargement, and because it's positive, it's an upright value. So again, the sign convention and understanding the actual physical nature of these mirrors and what it means to be behind or in front is going to be essential to your understanding moving forward. We're now going to deal with this idea of refraction. So hopefully you've done a lesson on Snell's law and this idea of refraction, whereby light will actually bend inside the material because the speed of light itself is slowing down. So there is this change in direction taking place. And so you can see that if we're talking about a converging lens, that all the light rays that are coming into the lens are actually going to focus on a focal point to the right of that lens. So unlike a mirror, the actual rays will pass through. But you'll notice that in this diagram, what we've done is we've put a line right down the lens, and we've bent those rays at that line. So don't just bend the rays once it hits the surface. Convention for these ray diagrams is going to be draw a dashed line right down the lens, and then draw the bent rays going towards the focal point or whatever it may be. a diverging lens, which is this object that looks like an hourglass, you can see that the rays are coming in towards the center, but then they diverge. They don't actually converge towards a focal point. But you'll see that to the left-hand side, or in front of this lens, we've drawn these dashed lines to represent these imaginary rays going backwards towards the focal point. This is going to be an essential tool when we go to draw the ray diagrams. You may recall that when we dealt with convex mirrors, that we used a very similar approach to find the imaginary or the virtual image behind the mirror. Well, in this case, because the rays didn't actually converge at a point on the right-hand side of this lens, the resulting image in a diverging lens is going to be an imaginary or virtual image. So if we take a look at converging lenses first, what we have to recognize is there's actually two focal points. And so depending upon which way the rays come, we're always going to be able to converge to within this focal point. And if the rays come from the right, the exact same thing is true. So you'll notice that in this case, then, we're going to actually label both focal points to the left and right of the lens itself. The distance has to be identical, so make sure that's true. Now, hopefully you've learned that to find the focal length of any lens or mirror, we're going to take a look at rays that are a long, long distance away, in theory infinitely far away, and what will happen is those rays will come in to the lens and converge at this point, which we'll call the focal point. So if you're ever asked the question, how do you find the focal point of an object like a lens, the answer is you focus on a object that is very far away, which allows us to assume that the rays are parallel coming into the lens, which will result in this convergence on the focal point. So when we go to draw ray diagrams, the process is going to be very similar, except for the fact that the image for a converging lens is going to end up on the right hand side of the lens. So you can see here that we have an object to the left hand side, and we have these three rays drawn. Now it's important that we label both focal points. It's important that we have this dashed line through the center of the lens, because this is what we're going to draw the rays to before the refraction is taking place. So again, as we did with mirrors, you can do it with 2 or 3 rays depending upon your comfort level. Honestly, at this point, 3 rays doesn't hurt anybody. So let's take a look at what this looks like then. We start with the first ray, which we'll label as the red ray. It's going to be parallel to the principal axis. It's going to get to that center point, and then it's going to refract through the focal point. The second ray is going to be one that goes right through the center of the lens. This is your blue ray, and you can see that it intersected our red ray at a point to the right. The third ray is this green ray, which goes through the focal point on the left-hand side of the lens, and when it gets to the center point of the lens, it now refracts to where it is parallel to the principal axis, and you can see that the 3 rays will converge on a point, and that will give us our image distance and size, and whether it's inverted or upright. So in this case, we know that because the image is to the right-hand side of the lens, that it is considered a real image. If we actually took this lens and put it up to a piece of paper, we could put the paper on the right-hand side, on the opposite side of the object, and we will actually see an image. We also see, though, that the resulting image is going to be inverted, and based upon the size of the image alone, we can see that it is actually going to be a reduced value. If we now take the object and we put it inside the focal point, what we get is a much different image, because in this case, our rays do not converge on the right-hand side of the lens. And so now we have to perform the similar type of ray diagram that we did with a convex mirror. And so we take the rays from the top of the object, and we first go parallel to the principal axis. This is the red ray, and it will refract and go through, but because of the lack of convergence on the right-hand side, we have to draw this dashed line backwards to represent this now seemingly virtual image that's going to form. Our next ray is going to be the blue ray. Now you'll notice that we've actually started it with a dashed line from the focal point on the left-hand side and followed it up on an angle until it hits the lens, in which case that ray would refract and go parallel to the principal axis. But because the image isn't forming on the right-hand side, we have to use this dashed line and put it backwards so that it intersects with our previous red dashed line. The third ray, again, is one that is not always important, but it's a great one to have just to verify that you've done it correctly. is this green ray which goes from the top of the object through the center of the lens itself. If we extend that ray backwards, we can see that there is now an intersection of 3 rays on the left-hand side of the lens, which gives us our image, which in this case I've put as a dashed arrow to represent the fact that it is a virtual image. So if we have a diverging lens, these are a little trickier, but what we can see that if we have an object on the outside of the focal point, our first ray, which is parallel to the principal axis, is going to refract away from the focal point on the right-hand side, but we can extend that ray backwards towards the left-hand side with that dashed line like you see. The second ray is the one that goes towards the focal point on the right-hand side. It's the blue ray, and you can see that when it gets to the lens, it's actually going to refract and go parallel to the principal axis. We extend that blue ray back, and we get the line that you see before you. The final ray, of course, is this green ray that goes right through the center of the lens, and you can see that all 3 of these rays intersect at a point which we can now label our virtual image. You can see just by the ray diagram that it is certainly reduced, but it is pointing upwards, which means it's an upright image. You'll notice that if we put the object inside the focal point, that the actual results don't change. So whereas with a converging lens we had 2 different results depending on it if your object was inside or outside of the focal point, in this case, regardless of if it's outside or inside the focal point, a diverging lens results in a virtual image that is upright and reduced. So the sign convention is again important. You can see here that we've made a table for you. We've excluded the magnification portion this time because it's exactly the same as it was before. But we can see now that we have to deal with this in front and behind the lens because we can have 2 different locations that could result in some sort of image being formed. Obviously, in the case of a mirror, if we were behind the mirror, that was considered virtual. But in this case, if we are behind the lens, what we will result in is an image location that's actually in front of the lens. So again, you have to recognize that there's 2 directions to lenses as opposed to 1 direction for a mirror. When it comes to the curvature, we're going to represent the radius as being a negative value in front of the lens and a positive value behind the lens. But when it comes to the image height, we know again that if it's positive, it's upright, and if it's negative, it's inverted. The same thing holds true for magnification, whereas a positive magnification indicates an upright image and a negative magnification indicates an inverted image. So let's take a look at this in action now. You can notice that I've labeled this as the mirror/lens equation because it really is the same equation for both. There is a different derivation involved for using lenses to derive this equation, but it is a similar result. In fact, it's an exact result. So our magnification equation and our mirror equation is also applicable to a lens situation. So if we have an object placed 35 centimeters in front of a converging lens with a focal length of 20 centimeters, we can calculate the image position relative to the lens as well as the image's characteristics by simply plugging in the values. Now you'll notice that in this case we have plugged in a focal length to be a positive value as we did the object distance. Well, that gives us an image distance of a positive 46.7 centimeters. When we plug that into the magnification equation, what we get is a magnification of negative 1.33 times. So the things that we notice again is that the object distance is positive, so it's a real image. We know that's inverted because the magnification has a negative value on it, and we know it's enlarged because this value is greater than 1. It's 1.33. If we ever have a situation where there's 2 lenses, these are the trickiest ones that you'll see, you just have to treat the image of the first lens as the object for the second lens. And so if we take a look at this complex ray diagram, you can see here that the first image that's formed by the lens on the left results in this I1, which I've labeled, which is an inverted and reduced image. If we now treat that like an object and create a ray diagram to represent the image formed by that object, what we result in is this inverted, enlarged virtual image. And so it is really just treating each lens individually, but the image of the first lens is the object for the second lens. One of the easiest things to notice about these diagrams is that we always converge the rays towards the focal point. But the question becomes, what happens if we don't converge these rays to the focal point? Well, if you've ever dealt with photography or any sort of optics in telescopes or microscopes, then you'll know that there are classic aberrations that occur when we're dealing with these optics. One of them is a spherical aberration. And what happens is, you can see in the diagram that all the rays coming in don't actually converge on a focal point. And so you can see in the images below that one of them is very sharp. That would be the example of all the rays focusing on the focal point. And the second image is now in the case of it being more blurry because all of these rays did not focus to a focal point. There are two primary ways in which spherical aberrations can be corrected. The first is to actually block out the rays that are causing this lack of focus, but in doing so it greatly reduces the actual brightness of the image itself. The more classic way in which we correct it is actually using a corrective lens. If you wear glasses, your spherical aberration is being corrected. If you heard about the history of the Hubble Space Telescope, its mirror was actually ground down to a point when it was out of focus, so that the astronauts actually had to go into space and correct it, or else we would not be able to see those nice, clear pictures that we've seen most of our lives. When it comes to chromatic aberration, what's happening is different wavelengths of light actually focus at different points. And so you can see the diagram again. We have some rays coming in, and once refraction's taken place, we can see that red light is focusing at a different length than the violet light. Well, if you look at the picture of the bird below, you can see the one on the left has this glow around it, this halo almost, and what that is the chromatic aberration taking place, as opposed to the image on the right, which is a perfectly focused, well taken picture. The problem lies in the actual index of refraction that varies depending upon the different wavelengths of light that come in. And since the focal length is dependent upon this index, what results is this out of focus image that we see. So the trick to fixing it now is to either increase the focal length or include some sort of achromatic lens to take care of this issue by having an index of refraction that doesn't allow this to take place. So it is a very important element when it comes to optics, and I encourage you strongly to understand these errors when they occur, and most importantly, how to fix them. So folks, that's it for the mirror equation, and that's it for lenses. I hope this has made sense. I would definitely practice your ray diagrams, and I'd practice the sign conventions and make sure that you understand which sign means what. And best of luck to you on your practice problems. We'll see you again.